Professor Detlef Lohse from University of Twente with us, delivering this particular talk as part of our MNBU Talk Series. Professor Lohse is a very accomplished researcher. He works on a variety of aspects of fluid mechanics. Many of you in this meeting would have already come across his work. He is editor of a number of journals and fellow of several societies and academies. He received his he has received several awards that we see here, including the Physics Prize from Dutch Physics Organization, the Bachelor Prize for Fluid Dynamics, actual Nobel Prize, and many more. And he was also knighted by the Dutch Queen. There are many more to talk about here, but I think without spending much time, I would welcome Professor Lohse again to deliver this talk.
Well, thanks a lot for this nice invitation. So today's talk is on droplets and bubbles with phase transitions. And where will the talk bring you? So I will address three subjects. First of all, freezing droplets. Then I will move to boiling droplets and explain the Leidenfrost effect. And then I will come to boiling vapor bubbles, specifically to plasmonic bubbles. So first on ice drop explosion. And this is a joint work with Sander Wildermann, Sebastian Sterl, and Xiao Sun. And here you see the reference. So what is this about? Well, first of all, let me point out the similarities between a good scientist and a good bird watcher. So here you see a good bird watcher. So as a good bird watcher, you must be curious, you must have good optical equipment, you must be very patient, and you must be at the right place. And finally, you must be lucky. With the right place, translating this to science, this means, for example, in our physics of fluids group in Twente. And for Sander Wildermann, all of this applied, and then for all this apply, you can make beautiful discoveries. And what Sander did is that he made this discovery. So he looked into drop impact under reduced pressure and found this. So here you see the drop, and it looks all very, very boring, but be patient. So here you see now an icicle growing out of this, and we were absolutely surprised to see this. Well, you are fascinating. You continue to watch what's going on, and well, be patient like a good bird watcher. And well, then you will see yet another surprise. So just be patient. Boom. So this breaks and explodes after some time. It's absolutely reproducible. And the question is, what's going on? Well, it's evaporative cooling, and we try to do this in a controlled way. So what we do is that we create some hydrophobic surface. We put a droplet on top of this hydrophobic surface, and then we reduce the pressure. And what then happens is that the water evaporates, and while evaporating, it cools down. So it's supercooled. And when you then initiated the freezing, the crystallization of the ice by touching with some silver nitrate, it freezes from outside in, and at some point it explodes. So it's really very, very fascinating. And here you see the controlled experiment. So we measure the temperature as function of time. So we reduce the pressure. Here you see the pressure in green. We don't have to reduce it that much. I mean, it's not vacuum. It's say 400 Pascal. And then we see temperature going down, staying constant, the drop being super cooled at -7 degrees. And at this point here, you in fact, you have this phase transition, and then latent heat is released. Temperature goes up to 0, but of course later goes back again. So the whole process here is 400 seconds. So you really have to be patient. So what happens? Well, what happens is that it freezes from the outside inward, and you in fact see this freezing front, and then some pressure is built up, and this pressure makes this block drop explode. So here I show you several snapshots. The ice nucleation here in the very beginning at time 0. So we put this moment at 0. Then you see this full ice shell. Ice expands when water expands when freezing. So ice has a lower density than water. That's why it's floating on the water. And therefore pressure inside the droplet will build up. And it will be so large that this ice shell will break and you get this ice spicule here. Well, from time to time you get some crack, but this heals again. And then it further freezes, and the pressure inside gets larger and larger and larger. So these guys grow, but the pressure at some point is so large that things will explode. And this is what you see here. So here you see the ice splinters, and now it's finally, after 2 seconds, it's fully frozen, and then the pressure is so high that the whole thing explodes, which you see here. So often it breaks into 2 parts, which you see here. Just prior to the breaking of the 2 parts, you see this picture. I mean, sometimes it smashes into several parts. So how exactly it freezes depends on the bubbles which are sitting in there and on contamination. So there is some variation from droplet to droplet. How long does the freezing process take? And what you have to balance is, you have to balance the quasi-steady heat flux through the spherical shell, which you can easily calculate here with the heat conductivity. And this is compensated by the heat generated at the freezing front. And this is, of course, determined by the latent heat Lm. And this, you just balance these two, and then you get a simple ordinary differential equation for the radius of this freezing front, starting at the radius of the drop and then going inwards. And when you now non-dimensionalize this in this proper way with this proper time scale, which is given by the latent heat and by the temperature difference, and of course, in particular by the size of the droplet, then you get this very, very easy differential equation. And when you rewrite it, you in fact can solve this analytically. So this ODE here, remarkably, I mean, it's easy enough that you can solve analytically. So this is the analytical solution of this ODE. And you can immediately see when the drop is fully frozen, then this radius is down to 0. And you see that in dimensionless time, the time is 1/6. So you immediately can read this off. And when you then translate this to dimensional units again, you see that the freezing time goes like r to the 2, r squared. And that's, of course, the freezing time for the front from going from the outside to the very center. But sometimes the pressure is already higher earlier. So when part of this water is not yet frozen. So this is, so to say, upper bound. And this is this curve here. So here I show you the explosion time. And this time that it freezes from the outside to the inside is this upper bound going like r squared. Those are the data. So indeed, they are all under this upper bound. So this is the data explosion time of the droplet versus the droplet radius. And in fact, we have some other bounds here. We have a lower bound here. This is incomplete freezing, but enough energy for this explosion. You can also calculate this. This is here. And you can also calculate the maximum elastic energy, which is then available for transfer to kinetic energy. And this is along this curve. And you see that all the data are nicely in between these bounds. So let's look into the explosion dynamic, what's happening. So the front is freezing, and you build up pressure inside the droplet here. And this results in some tensile strengths here. Once this tensile strength is large enough, the ice can no longer hold it, and then the whole thing breaks apart. And this tensile strength of the ice, of course, goes like R cubed. Here I put in some elastic bulk modulus of the water and the tensile strength of the ice, which is about known. This, of course, depends on how exactly you make the ice, so there is some variation in this. And this elastic energy goes into kinetic energy for the breakage and for the surface energy. Kinetic energy, of course, goes like R cubed, but also like velocity squared, with this typical velocity of these parts flying apart. And surface energy goes like R squared. And for large droplets, you can neglect the surface energy, and then elastic energy directly goes into kinetic energy. And out of this balance, you can calculate the ejection velocity of these ice particles. And what you get out of this is about 1 meter per second, and this is exactly what we observed, order of magnitude. I mean, it's an order of magnitude estimate, of course, but it works very nicely. So what happens when you go to smaller drops? Well, that's extremely relevant because apparently in clouds, you have these super cool droplets, which are at temperatures -4, -5, -6 degrees. And then what is observed is that all of a sudden, these droplets transfer into ice. And this was not understood up to now. Why is this happening so rapidly and so violently? And it could be that this process plays a role. So for this very small droplet, the required surface energy is, well, for the small droplets, you need kinetic energy, and then you balance the elastic energy with required surface energy, and then you can get the minimal size for the explosion. This is 50 micron. And in fact, this was in this drawing here, which I didn't show you before, but if you zoom in, you see that below 50 micrometers, this process cannot happen. So only for these larger droplets. And this apparently plays a very important role in the formation of hail and ice out of the supercooled clouds. But why is it happening all of a sudden? Well, there's a cascade process. So I showed you that you need some initiation of this process, and we do this here with the silver nitrate crystal. So this is touched, and this is exploding, and ice crystals are then touching this other droplet. And there they initiated the freezing process. So up to then, it was only supercooled, but then it's initiated, this process, and you see it's freezing. Pressure builds up, these icicles form, and at some point, this guy will also explode here. So there's really a cascade process. Once that you have one, you get explosions, which are very sudden. So this guy infects this guy, and then is basically the whole cloud is turning from supercooled droplets to ice. So that we bumped into all this purely incidentally. And I mean, it shows the beauty of fluid dynamics. So we looked into evaporating droplets and freezing of droplets, and it turned out that we found something which is highly relevant for climate, cloud formation, weather, and so on. So this shows the universality and beauty of fluid dynamics. But now I want to go from freezing to boiling, and from droplet impact towards droplet impact on superheated surfaces. And this is what you see here. So up to now we had supercooled droplets. Now I have superheated surfaces, and I let droplets fall on it. And on the left, you see a droplet falling onto a surface of 380 degrees. And then you have touchdown and boiling. So here's the side view and the bottom view. Whereas on the right, the temperature is higher. It's 540 degrees Celsius. And there the liquid doesn't make any contact to the substrate. So here we have the dynamic Leidenfrost state, no contact at all. And the application of this kind of phenomena is tremendous. So spray cooling, for example, where you really don't want to be in this Leidenfrost state, but you want to be in this state to have maximum heat transfer, but also for spray combustion, all this is absolutely crucial. So we call this here the dynamic Leidenfrost effect because we let the droplet fall on this. So the static Leidenfrost effect has been known for long, in fact, since 1756. And here you see what was done. So Leidenfrost took a droplet, put it on a spoon, and then on a hot spoon, and then let it float. And this droplet is supported by its own vapor. You see a sketch, floating droplet with the vapor, and then the lifetime is very large. In fact, what he did is he did lifetime measurements as function of the heating, and then he found this transition from the droplet in the contact mode to the droplet in the floating mode. So here you see Leidenfrost. Unfortunately, I didn't find a more friendly picture of him, well, he had quite some impact on the field and found this beautiful phenomenon. So let's go to this dynamic Leidenfrost effect, and here you see some references. So here you see the sketch of this impacting droplet. And what happens is that at impact, some pressure builds up under the droplet and deforms this droplet. So you get this dimple. So here you see with high-speed interferometry what's happening. The droplet is falling. You get a dimple formation here. And out of this interferometric information, we can extract the distance of the interface. So here, in fact, you see how we do this. We do this, in fact, with high-speed color interferometry, which is very, very good to extract the profile. So here you see the profile H in micrometer and the lateral scale in millimeter. I mean, note that this is strongly deformed, so there's a factor of 1,000 in the scale or the less as compared to the scale here at the bottom. And so out of this, we extract the droplet, the dimple size. In fact, this is the volume of the dimple, of the bubble, divided by the volume of the drop, versus the Stokes number. The Stokes number is basically the non-dimensionalized velocity. So here I also plot velocity, and here I plot the absolute volume of this entrained bubble in picoliters. So you see it's tiny. And what's most remarkable is, on first side of this plot, that without any parameters we can calculate this, and how we calculate this I show you in a second. So red is experiment and blue is simulations, and we have two regimes. We have a capillary regime on the left, and we have an inertial regime. So when you very gently deposit the droplet on the substrate, you don't get much of deformation, and the entrained bubble is very, very small. And on the right, you are in the inertial regime. There you smash the droplet against the surface, and also there you don't get much of an entrained bubble. But in between, you have a maximum. And look how pronounced it is. You can also calculate the scaling laws here and the scaling laws here simply by balancing the forces. And the applications of this are huge. So, for example, immersion lithography. We have a collaboration with ASML, this chip producer. They clearly don't want to have entrained bubbles inside their droplets for immersion lithography. But also for inkjet printing, it is extremely relevant, or for coating, because these bubbles which are entrained change the optical properties of those droplets. So all this must be understood. And thanks to experiments of this type, we really understand this on a fundamental level. So how do we calculate this? Well, I can't go into detail of this. There I must refer you to the paper. So the parameter space of droplet is huge. So you have the properties of the droplet itself, the type of liquid, the radius, velocity, the shape at the impact, the temperature. Then a crucial parameter is the surrounding gas type and the gas pressure, and of course various surface material properties. And we clearly can only scratch on the surface of all this. And in this talk, I will touch upon these red properties and show you the dependencies. So on the method, so how do we look into this? So experimentally, so I already showed you this high-speed color interferometry, but what we do in addition to look into even closer distance between the droplet and the substrate, we apply total internal reflection. So the principle is shown here. We have this prism, light comes in and light is reflected at this prism. And the way how it's reflected, of course, depends on whether there is no droplet here or whether there is a droplet here. And with this trick, we can really probe the first, say, 10, 20 nanometers of this droplet, whether there is contact or not. So this is really the resolution which we can achieve. So here you see the full experimental setup. We have the droplet falling on the substrate, and we have optical equipment, and we have this prism. And well, we need this heated prism because we want to look into Leidenfrost and then look what's going on from the bottom view here and also from the side view. And here you see some experiment with TER. This is FC84, which is a special liquid with low latent heat. And we let it fall on sapphire below the Leidenfrost temperature. And what you see is that you see all these boiling events here all over. So it's very, very complicated. Well, here some other examples. So now we have the droplet falling on glass. And what you get this thin film of liquid, and this thin film then breaks. So you see here all these droplets emerging. So first, when it falls down, so this will play again, it spreads. So here you see the spreading, and you have this thin film. It breaks, so here bubbles form, and then you have this Taylor cooling retraction, and you end up with these droplets. So here I show you the snapshot, typical snapshot as a function of the temperature for ethanol on glass. Up to here, you are in the contact mode, and here you are in the no contact mode, so in the Leidenfrost mode here. So this is how things depend. I mean, here in the middle, you still have some little contact, but you have the lamella, and here at 400, no contact whatsoever. So let's look into the correlation between what we see at the side and from what's the bottom. And at 25 degrees, things are fully correlated. So from the side, we look at the lamella here, and from the bottom, we get these red data points. This is the contact area with total internal reflection. And at 25 degrees, this is just the same. What you see from the bottom is the same what you see from the side. However, when we now go to the 250 degrees Celsius, you see that the lamella is spreading much faster as compared to the contact area. So you get partial detachment. So in red, I show you the contact area here in this movie, but the lamella is much further out. So you get partial detachment. So you get the situation which looks like this. So in contact boiling, you get this regime. This is simply spreading. And then you have, on the other hand, the other extreme, this is Leidenfrost boiling, no contact whatsoever. But in between, you have a partial wetting region in the middle, and you have this levitated region here. So this is the state in between. The nice thing about TER is that we can extract quantitative information here. So it's the side view and the bottom view at 150 degrees. And the color here is, the color code is given me. This is the distance in nanometers. So you see red means contact, so 0 here, and blue means very far away. So this is at 150 degrees, simply contact. You see some bubbles right here, but that's about it. When we go to 107 degrees, you see many more bubbles here. This is, by the way, at the top, it's the original paper, original picture. Whereas at the bottom, we have out of this picture here, we have this information extracted. And when we go further up, we see that in the middle, there is this dimple here. So very much the same what we see without boiling. So there is a ring of contact here, and in the middle you have this dimple at 180, and when we go to 220, there's no contact whatsoever. So the droplet is always more than 80 nanometers away from the substrate. So here's the phase space, impact velocity here, and temperature here, with this contact boiling regime right here, the transitional boiling regime here, and the Leidenfrost boiling regime up there. The question now is, how does it depend on the liquid properties? And here I show you this phase diagram for ethanol, which you saw before, and here I show it for FC84, one of these cooling liquids. And what you see is that it shifts down quite a bit. So the Leidenfrost state here is only achieved at much higher temperatures as compared to here. The question is, what is the material property which is different? And it is, of course, the latent heat. So ethanol has very high latent heat, whereas those liquids here, these organic liquids, they have very low latent heat. So here, so to say, to get into the Leidenfrost state, you must pay much, much more, and therefore this is much higher. So what is the dynamics of this neck for this Leidenfrost case? Here you see this neck in the middle of the dimple, and you get to touch down at the beginning, and when you touch down, this liquid boils away, and this neck is visible thanks to this evanescent length scale. So here you can see this the situation. So in the middle you have the dimple, and here is the neck, and heat transfer is, of course, in particular here, because here you are closest. Here it's always isolating, and this has quite some bearing on how to model this. The dynamics of the neck is just the same as the dynamics of the neck for the cold case. So basically, it goes like radius goes like square root of t, that you can understand. In fact, this is kind of understood since the 30s in the context of a boat on the ocean with water waves. So there, Wagner calculated some theorem on this radius as function of time, and it's all inertia dominated, and this is exactly what's going on here. So this goes like square root of t, and well, I won't go into this here. But the interesting thing is in the middle. So here with this dimple, and when you want to model the heat transfer from the substrate towards the droplet, you must, of course, know what's going on here. The main contribution for evaporation comes from here. And well, I must admit that in 2011, we were not so much aware on this. And then I came up with the pancake model to somehow model the evaporation, which looked like this. But in view of these results, I must admit that this pancake model is not the greatest. And proper modeling of the heat transfer can only be done once you take this geometry here into consideration. So very different time and length scales are at play. So this was the effect of the liquid, but now what's the effect of the substrate? We want to compare glass versus sapphire, which has very different thermal conductivity. So here you see the impact on glass for different temperatures, the glass impact here. So I've shown similar movies before. Now what's happening for impact on sapphire? Well, here is ethanol in both cases. On the left you have glass, and on the right you have sapphire. And what you see is that for glass you achieve Leidenfrost only at much higher temperatures. So here typically we have 300 degrees Celsius, whereas on sapphire you already have a Leidenfrost effect at 220 degrees Celsius. So it's a huge difference. And the difference is, of course, that the heat conductivity of glass is much, much worse as compared to the sapphire case. So the droplet falling on the substrate partially cools, and this is seen here, whereas for this perfectly conducting case. It is not seen here. So the origin is that the thermal timescales differ, and the thermal timescales, in fact, are known since the 70s or even the 60s. There's this very nice paper from 1973 where they calculate the timescale for the thermal timescale, which is in fact composed out of the thermal conductivity of the substrate density, specific heat of the substrate, and the heat transfer coefficient from substrate to drop. And this timescale must be compared with the dynamic timescale of the impact, droplet diameter over the velocity. And if this dynamic timescale is larger than the thermal timescale, then you have a cooling effect, and then the Leidenfrost temperature should depend on the substrate. If this guy is smaller, then there should be some independence and you have some ideal substrate. So then you have the solid is then isothermal, and well, enough energy is always on the solid to keep it at constant temperature. When you now look into the numbers of sapphire versus glass, you see that there's a huge difference in thermal conductivity here, sapphire versus glass, a factor of 32, and resulting in a huge difference in thermal diffusivity here, and therefore resulting in a huge difference in the thermal timescales here. So the thermal timescale for sapphire is 50 milliseconds, and for glass it's only 0.3. And when you now compare it with the impact timescale, which in our case is about 1 millisecond, you see that you are in two different regimes here. So at sapphire, you have, so to say, a thermally perfect impact, whereas glass, you don't. Therefore, you need higher temperatures of the substrate to achieve Leidenfrost state. The question is, can you measure this? So how much does the droplet cool down the substrate? And in fact, Michiel van Lumbeck, he did succeed to measure it. I must say, I was pessimistic about it. So the aim was to measure and to calculate the cooling of the surface by the Leidenfrost droplet. So here you see the situation. Here we have our liquid droplet, and well, here you have the heater and TH, but the temperature up here, where you are in closer contact to the substrate, is lower. And can you calculate this and can you measure this? Well, on calculation, I was optimistic. On the measurement, I was pessimistic. And what Michiel did is that he did succeed. He can't measure it dynamically, but what he did is that he put a droplet in a, so to say, a static Leidenfrost droplet. He had a droplet fixed above the substrate and would feed the droplet in a way that the loss by evaporation is compensated by influx of this droplet. So he so to say has a quasi-static situation, and with this he has enough time to measure. So indeed my pessimism was justified with respect to the dynamical measurements, but my pessimism was not justified with respect to static measurements, and Michiel van Lumbeck really did a wonderful job in measuring this, as you will see in a second. So this is a quasi-static case, and well, the heat conductivity then is given there. Liquid droplet has the temperature here at the saturation temperature, and we have some vapor layer in between. And Michiel's idea was to use Mach-Zener interferometry. So the refraction index depends on temperature, and hence temperature difference results in some differences in optical path lengths, and you get fringes. And here you see the principle. So you have the test section, so you either go this way or this way, and there's a different optical path, and out of this you can extract the different temperatures there. I mean, it's highly complicated. So here you see the setup with this trick of Michiel to put this droplet close to a needle. And this needle has two functions. First of all, it avoids that this droplet is wiggling back and forth. And second, it feeds the droplet so that the evaporation loss is compensated. And what we do is that for the droplet, we simply put in the global droplet shape, which is given by Young-Laplace equation here, with gravity playing a role. So gravity is compensated by capillarity. And then we have a lubrication approximation for this layer under the droplet. That's the standard approach here. But what we have to add is this Fourier law for the heat loss here, for the heat loss towards the substrate. So that we couple. So this is the viscous lubrication approximation. This is standard. I mean, that we had done before to calculate the gap of the droplet, of a cold droplet. I mean, this is why I referred you to the physical regulator where we did this Bauhaus et al. Paper from 2012. But now we add this term here, and with that we can calculate the temperature. And this is the result here. So we assume axial symmetry, which is justified. And on the left, we show the numerical results, and on the right, the experimental results. And again, there's no parameter in here. And the temperature scale is given here. And it's not bad. I mean, it's not perfect, but it's really not bad at all to see this behavior here and the cooling down. The cooling down is considerable. You see here, we cool down to 240. Down here, it's 320. This is to what we set the substrate, but here it's cooled down to 240. And when we now compare the curves here, the solid curve experiment and the dash curve is numerics, now for different droplet sizes, and it's not bad. So, I mean, you see this cooling down right here, and this is also in the other curves here. So in the numerics, we clearly see the dimple here in the middle. In the experiment sometimes, but I mean, there is some wiggling, so the dimple in the middle is a little bit washed out in the experiments. But I mean, I'm particularly glad that this cooling down effect can be calculated. So let's summarize on this dynamic Leidenfrost effect. We have extended transitional boiling regime. We get this dimple structure. We studied the effect of the latent heat and the effect of the substrate and also the effect of the surface cooling due to this droplet. And this can be measured and calculated. The question now is splashing also possible for this Leidenfrost droplet without any contacts? And indeed it is. So here we see the film boiling regime. This is the bottom view. So there's really no contact, but we do see splashing. And the reason for this is that the gas in between the droplet and the substrate is floating outwards, and then it takes liquid along. We now go to parameter space, Weber number, which is basically the impact velocity, versus temperature. We have various regimes. I mean, first of all, we have the regime where we have contact. So this is the transition temperature to film boiling, and in this case, it's about 160 degrees. And then here we have, in this regime, we have deposition, and here we have contact splash. Splashing, because the spreading of the contact line is so fast that at some point you get instabilities. This can also be triggered by some roughness. But all this roughness is not relevant in this regime. So here you see that when we are in the Leidenfrost state, this point of splashing goes down quite a bit. I mean, nearly by half an order of magnitude. So here in this regime here, you have bouncing of the droplet, so no contact whatsoever, but the droplet keeps its integrity. Whereas here you have the film splashing. So no contact and splashing. This is due to the gas flow or the vapor flow going outwards. And well, this gives us beautiful pictures, which you see here. Now from the boiling vapor bubbles in a drop, we go to a hot surface or to plasmonic bubbles, and you will see that the heating now the heating is not by a surface, but the heating is by a laser light. This brings me to these solar steam nanobubbles. I bumped into this paper here in 2013. They postulated solar steam nanobubbles. And what happens is that they put in nanoparticles. And these nanoparticles have a so-called plasmonic resonance. So they heat up quite a bit. Then around these particles, vapor forms. And what they claimed here in this paper by these chemists is that this would be a very cheap way to generate a very hot vapor. So simply put in nanoparticle in some liquid or some suspension, put it into the sun, and then vapor would be formed. So, there was this perspective in ACS Nano, and I was very, very skeptical about this. And well, you will see why. There are also other applications of these plasmonic nanobubbles in medicine. So you can put in these plasmonic particles inside the body and then shoot with a laser. The particle then will absorb the laser light, and around this particle, some bubble is formed. So our approach was, let's look into these plasmonic bubbles under highly controlled experimental conditions, and this led to a series of papers. So let me ask, how much time do I have? So as there are two possibilities.
Well, we are fine with time. I mean, you can
I can continue with this. Okay, well, then I will go through this. So I have, say, 10 more minutes or 15 more minutes?
Yeah, 10 should be fine.
Okay, good. Well, how do we prepare the gold nanoparticles? So this is done in the clean room. The nanoparticles are typically 45 nanometers in diameter, and we place them on some substrate. So here you see pictures by SEM, scanning electron microscopy, and by energy selective backscatter. And that we then place in the liquid here. So it's sitting right here. And we look from the top with high-speed camera, and we also look from the side with high-speed camera. And we couple in the laser towards the particles, towards so that we can heat those particles and create these bubbles. And the key control parameter is the laser power here. And the other key control parameter is, in fact, the gas content of this liquid. So what in this Haller's paper was not mentioned at all is the amount of dissolved gas in the liquid. And well, we had looked at many bubbles, and I know that for this bubble formation, the amount of dissolved gas, so dissolved air, is in fact pretty crucial. There's a huge difference between vapor bubbles and between gas bubbles. There's, by the way, also a very nice annual review of fluid mechanics on this by Andrea Prosperetti. There's a huge difference, and many people confuse vapor bubbles with gas bubbles. It's totally wrong. Vapor bubbles are controlled, in fact, by thermal diffusion, whereas gas bubbles are controlled by mass diffusion. And we all know that between thermal diffusion and mass diffusion, the diffusion constant is different by a factor of nearly 1,000. So it's a huge difference. And this will play a role, as you will see. So here you see the emerging bubbles, and we have radius, we have the angle, and there are, in fact, several nanoparticles under this emerging vapor bubbles. And here you see what is our observations on a long time scale. So this is now a time scale of 5 seconds, and you see emerging bubbles on the left for water which contains gas, and on the right for water where we partially degassed. And this is what you see here, and you see that for the gaseous water, the growth of this bubble is much, much longer, whereas here it ceases at some point. So quite different behavior. So already here we see that gas plays a major role. When here we compare now the radius as function of time for gas rich and for gas poor. And for gas rich, it simply grows and grows. And for gas poor, it comes to some saturation. For the gas rich case, the growth is simply linear in time. This is perhaps what you would expect. And for gas poor, you get that the growth stops. And It plays really a major role. And the question is how to understand these scaling laws. Radius of T going like T to the 1/3 for the gaseous case. For the degas case, basically it's constant. I mean, if you measure and if you fit, you find T to the 0.07. But well, I think that there's still some little gas in there. So we would expect that it simply goes to some stable size. So it's not diffusive, as you see. So naively, you may think it's diffusive, that radius of T goes like T to the 1/2. No, this is not the case. Well, here it goes like T to the 1/3, and I will explain this in a second. So here I have this compensated plots. T to the 1/3 is really pretty nicely fulfilled up here when I compensate. So if radius divided to T to the 1/3, so here this is constant. So how to explain this? Well, simply the volume is linear in time, and it's simply outgassing. So what happens is that this is, so to say, a production-limited growth process. You outgas the water by simply heating it. So by heating, you decrease the solubility of gas in water, and therefore the water has not much of a choice but to expel the gas. And where does the gas go? Well, it goes, of course, to this nucleus, which has been formed by boiling, to this vapor bubble. So in the beginning, you have a vapor bubble, but then the liquid around the bubble warms up, can take up less gas, and therefore you will have growth of this bubble. And then the constant growth rate implies that the volume simply increases linearly in time. So the radius goes like T to the 1/3, and you put up the energy balance, laser energy being put in, and the heating of the water, and out of this you can even calculate this prefactor here of this growth process. And this is directly related to this power. And when we now look into this prefactor here, which we get, it also is pretty consistent with what we would expect, how that this prefactor is linearly connected with the power which we put in. The conclusion on the long time scale is that the solar steam nanobubble is nothing else than hot air, literally speaking. But what about the short time scale and the very short time scale? So, well, the initial phase of contact on the short time scale behavior, there's not enough time for the gas to go into the bubble, and then for the short time scale behavior, so it's now not 5 seconds as before, but is 100 milliseconds, then they simply grow and gas is formed, and it is the same. So I won't go into this because I want to spend time on the others. So they can derive, in fact, the radius goes like T to the 1/6. When you balance the laser energy with the heating of water, for the long scale, on the short time scale, you balance the laser energy with water evaporation because it's dominated by evaporation. And when you all do this, you get, in fact, the radius goes like T to the 1/6. So the question is, where do you use your laser energy for? Well, in the long term, it's for the heating of water, but in the short term, of course, it's for water evaporation, and then you get this radius goes like T to the 1/6. This is this phase around here. So the early times, radius goes like T to the 1/6, and then later for water with gas, radius goes like T to the 1/3, or it's about constant if there is no gas. But the big question is now, what's happening? Well, this is what I explained to you. Here's vaporization dominated, and here it's dominated by outgassing because you heat the water. But the question is, what's going on right here in the very, very early phase? And this is what I would like to show you now, which I think is the most interesting thing. So what happens in the very early phase at very short time scales? So it's microseconds. So first I talked about seconds, then I talked about, say, 100 milliseconds, but now I go to microseconds on bubble nucleation. And we are pretty much the only one who can look into this because we have this high-speed camera with 25 million frames per second, and we can really look at the very, very early phase. And this is what we see. So we see this giant bubble generation here. So here we visualize it with 8 megahertz, 8 million frames per second. And then we see this huge giant bubble at the very beginning. And well, later we get some oscillation bubble here. I won't go much into this, but I would like to go into this, what's happening. So when we look into this bubble, this giant bubble, on a time scale of microseconds, we see that it gets huge, 40 micrometers radius here. And well, the later bubbles are all much smaller here. So if you compare this initial giant bubble, this is 60 microns typically, whereas later these oscillating bubbles are around 10 microseconds. It's still not the bubble which then grows because of diffusion and outgassing. So this is only at the very, very first moment. So you see after 10 microseconds, it's already gone. So without a high-speed camera, you don't see it. And the most remarkable plot of this whole talk, I think, is this plot. This is the size of this giant bubble, the giant vapor bubble, as a function of the control parameters. And I said the control parameters are the laser power on the one hand and the gas content on the other hand. And you get two huge surprises. So first of all, you see that when you increase the power of your laser, the size of this vapor bubble goes down. And this is just remarkable. You would think more power of the laser, larger bubble. It's not the case. It's a smaller bubble. What you would also expect is that when you add some gas, then you should get larger bubbles. But this is not the case either. So the red curve is the gas-rich case, where you say, okay, well, it's more gas, there should be a larger bubble, but this is not the case. So the gas-poor case creates a much larger bubble as the gas-rich case. So there are two huge surprises, and I will now explain you why this is the case. And the key is the delay time. It is the delay time between turning on the laser and between nucleation of this bubble. And you see that the delay time for the gas-poor case is much longer as compared to the gas-rich case. And you also see that the delay time goes down with increasing laser power. And the reason is that you go in phase transition. In this phase space, you go from the stable liquid, you go towards the vapor phase. And then here you're in this regime where you're superheated. If you're superheated strongly at some point at this liquid spinoidal curve, clearly you get nucleation of a vapor bubble you can't avoid. But in this regime in between, you can be superheated. And the question is, when is the superheating state going on towards the bubbly state? And this, in fact, happens earlier for the gas-rich case, because for the gas-rich case, you have more little crevices and little gas bubbles around. So you nucleate the vapor bubble earlier because you have more nuclei. And for the gas-poor case, you can superheat in a much stronger way. So this nucleation temperature, of course, does not depend on the laser power, but this implies that this delay time does depend on the laser power here because of this, what I explained on the number of points which are around, and therefore it strongly goes down. And what in fact is relevant for the growth of this bubble is not the laser power, but it is the energy which is dumped into the system. And this is the laser power times the delay time, because here things can accumulate. The energy around the bubble can accumulate. So what's the relevant parameter is the laser power times the delay time. And here I calculate this energy pumped into the system versus the power. So taking this delay time into consideration. And when I now plot this energy dumped into the system versus the volume of the bubble, I get this beautiful linear relation. This is exactly what you expect. So whether it's gas poor or gas rich, doesn't matter. You have this linear relation between the size of the bubble, the volume of the bubble, and the energy, and the delay time is really very, very crucial. And we can even calculate the slope here of this relation. And what we now do is that we calculate the achieved temperature. So this is simply diffusion. We have the sources here by the nanoparticles, and we have thermal diffusion of this power around these particles. And well, we superpose the temperature fields from all nanoparticles, and we can reconstruct the temperature field. And out of this, we can then calculate the curves and reconstruct the temperature. So here is the delay time as a function of the power. This is the liquid vapor line here, which corresponds to 100 degrees Celsius. The spinoidal curve is up here, but those two curves which we measure are in between, and out of this we can in fact calculate the temperature with this trick. So for the gas pure case, we achieve 500 degrees, so nearly the spinoidal temperature, whereas when there are many air pockets in there, nucleation is earlier, and then the nucleation temperature is only about 420 Kelvin. Yeah. So when we calculate the conversion efficiency, in fact, it's very poor. So it's about 4%, whether it's gas rich or gas poor, and it's not very efficient. I mean, most of this energy goes into heat, in fact, and well, so this is not a wonder to create vapor in a very efficient way. Basically, you heat up your water, and well, a little bit vapor bubbles are created, but well, then they are in fact filled with gas. So the summary of this experimental part on this bubble. So the first phase is a giant initial bubble. You have bubble nucleation through the competition between laser heating and diffusive heat loss. And you get this very counterintuitive result on the maximum volume of this bubble. And you can resolve it by calculating the delay time, which determines, in fact, the energy bumped into the system. And then you get this relation, energy bumped into the system is proportional to the maximum volume of the bubble. This is what you expect. This is the very early phase, and then later you have this oscillating bubble, and with benefits from these air pockets. I mean, once this has happened once, of course, you have all these air pockets, and then it can happen easily later. And then you have vaporization-dominated growth, and finally you have growth by outgassing that we all summarize in this paper. We also did this numerically here with MD simulation. I show you this simulation by Shantanu Maheshwara. I don't have time to go into this, but we redid this also with MD. So I would like to summarize these four phases here. Watch that all movies have the same length scale here. So time scale is, of course, very different. Here we have microseconds, here we have milliseconds, and here we have, well, up to many seconds. And this creation of bubbles by this plasmonic event is so rich that on all time scales, it has really beautiful physics to offer. And with this, I end. So let me acknowledge my co-workers and fundings. Of course, this is work over many, many years with many co-workers. So in particular, I would like to highlight Michiel van Limbeck, who did these experiments on the Leidenfrost effect, and on Leidenfrost also Tuan Tran. Julian Wang, he did these experiments with the plasmonic bubbles, and while Sander Wildemann, in fact, I acknowledged already in the beginning on this freezing droplet. What I also would like to acknowledge is that we have PhD and postdoc positions available. Just send me applications. So the group is, in fact, not me. The group is hungry young scientists who are very enthusiastic of doing science, both theory and experiments and numerical simulations. And we have several vacancies. Send me some applications. Well, it is really the PhD students and the postdocs who make the group. I was also asked to announce this call for papers for the first Indian conference on micro nanofluidics, from soft matter to bioengineering. And I would like to end with this summary here, and I'm happy to take questions.
Thank you very much, Professor Lohse, for a very insightful talk. I think, it was with a lot of details and insights, and also, showing us things that I don't know how many of us have access to a 5 million frame rate per second camera. So thank you for that. So now we can open for questions. The audience can unmute themselves and ask questions, and I would moderate the sequence.
Hi, Professor. So I wanted to know how the pressure inside the ice was measured for the first case you was showing, the ice drop explosion.
It was not measured. So we measured the temperature with the thermocouple. The pressure which I showed is the pressure, the ambient pressure. So we reduced the pressure. So we didn't measure the pressure inside the ice. We only measured the temperature. So the curve which I showed is the pressure, the ambient pressure, which leads to this evaporative cooling.
Thank you. I have one more question. Is about the Leidenfrost effect problem. So you showed that for 540 degrees Celsius, the drop doesn't really touch the substrate at all. So what is really, I mean, the time scale that the Leidenfrost effect needs to ensure that there is enough thickness of the vapor to ensure that the drop doesn't touch the substrate? Like how fast is it?
Well, it's a very good question. So let me go back to those slides. Let me see how to do this best. Well, perhaps I can go out and go there directly to show those cases. You indeed see here, for example, well, this point. Let's see what's maybe. Well, perhaps I show this here. So let me show this. So here you see milliseconds, and here you see in the first moment there is some more contact than later here. So let me. Well, here you see in the very first case, this is say milliseconds, so microseconds. You see some contact right here. So and later this is gone. So in the very first moment, there is contact and well, a little bit more contact, then it's evaporated. And well, this is in fact on a time scale smaller than 1 millisecond. And then later it's evaporating and you don't see any contact anymore. So it also depends on the impact velocity, of course. The higher the impact velocity, the more you force your liquid towards the substrate. But it is in the range of milliseconds. So, and then within milliseconds, the equilibrium can establish.
Okay, thank you.
More questions?
Yeah, Detlef, Cam here. I was a little bit surprised. We also published that the substrate and its thermal conductivity is more or less determining the Leidenfrost point. And we use the effusivity. You didn't mention the effusivity. It seems to be that would be the parameter. You talked about the thermal conductivity and the thermal capacity, but isn't the effusivity actually the parameter you want to use to more or less say how fast can the substrate deliver the heat into the vapor layer?
Well, I mean, you can calculate one and the other. I mean, here we use as control parameter, we used the thermal conductivity of the substrate. Well, it's really the time scale of the transport of heat in the substrate.
Exactly.
Which
but that is the effusivity.
Yes. Yeah. Well, I mean, I translate this. I mean, in a sense, I mean, the control parameter for us is the thermal conductivity. So we have these two cases, and then I translated this according to this Baumann paper, into that time scale. So yes,
Yeah.
it is this time scale which determines this. Yes, no, I agree. I mean, but well, I mean, our case, well, we simply, well, the control parameter which we varied was the thermoconductivity, and these two cases. So.
Yeah, I think with the time scale is nice because then it tells you, okay, whether it's going to play a role or not, the substrate. But okay, we cast all of our results with the effusivity, and then
you express this, and I mean, this is the time scale.
Both are very good.
So the dynamical time scale with this thermal time scale, and well, that's a relevant comparison.
Yeah. But I think it's at least it's now well established that there is not a Leidenfrost temperature.
Yes, I fully agree. No Leidenfrost temperature.
Determined by a lot of other parameters.
Yes, I fully agree. There's no Leidenfrost temperature at all. I mean, it also, in fact, depends on the procedure. So when you in fact want the Leidenfrost state, and then you reduce the temperature, you can keep the droplet in the Leidenfrost state. So we did recent work with Pierre Chantelot in Twente, and well, where we have this picture that we see this transition from the Leidenfrost state towards the touching state, so the other way around, some direct percolation process, and that really depends on all kind of disturbances and so on. So it's really, there's not one single Leidenfrost temperature. I mean, there is a maximum and there's a minimum.
But this is something that's really only come out over the last few years. That's
I think it's super interesting.
We call that state the thermal super repellency, thermal super repellency. We call that that intermediate stage.
Yes. Yeah, people were hunting for Leidenfrost temperatures basically for centuries. But now we see there is no Leidenfrost temperature. So there is a whole range, and depending on the procedure, it is one or the other. And yes.
And the substrate, yeah, I can only agree. Unfortunately, I missed the first half of your talk because I didn't have the slides in front of me, and I went out and came in again, and then the slides were there. So I won't ask you anything about the icing.
I can send to you. So, or I can come to Darmstadt and give a talk there in person. So.